cross B, A cross B, so we know that this guy is going to point off in that direction, perpendicular to both of them. And that, if we negative 2x hat plus y hat, oh no, I forgot a 6, plus 6y hat plus z hat. All right, we've got negative 1, or where's x? Negative 1, 2 in x, right? We've got 6 in y, and we've got 1 in z, bringing us to that vector. Okay? That might be one of the better pictures I've drawn, actually. Small accomplishments. Okay. So, let me check the time. Yeah, oh, we got lots of time. I'm going through this really quickly since no one's asking questions and it's not as much fun to tell stupid jokes or stories because there's no one there really to listen except for my cat, who is asleep again. Lazy cat. Okay, so now returning to torque, we can write our full definition of torque. So I'll write with the impressive looking triple equal sign, very authoritative. Torque is defined as R cross F, right? The radius cross the force that's applied. So this force, if I wanted to be absolutely completely clear, is the net force applied at that point R. Right, so we could even put a little F subscript there, and maybe a little F net subscript there, okay? So F here is the net force vector, not a component, and R is the position vector to where the force is applied. So if I had some object, right, let's say that this disk-like object is having a force applied to it, right, at some particular position. This would be R, this would be F. I would take the cross product of those two vectors, and that would give me the torque. So the way I have it drawn, I would move this vector, over here. Right, I have R cross F. I'd have my torque pointing in that direction. Okay? So that's our full definition of torque, and I'll get you guys some problems when I figure out how to do that for just calculating them. But taking the cross product of these two vectors should be fairly straightforward. So with our remaining time, I want to begin to define angular momentum. So angular momentum will take us a couple more classes to define in full, but we start off with the basic definition, right, which we can do now that we have the cross product. So angular momentum, which we write with capital L, is R cross P, the momentum. Right, so what we're doing essentially is going through all those concepts we built up from linear mechanics and finding versions of them that work for our rotational mechanics, right? So we found first our definition of rotational kinetic energy, and then we talked more about rotational motion, and then there was the thing torque that's like force is for linear motion, and now one of the concepts that we're still missing is momentum, right? Those are the big things we need to define in mechanics. We need forces, we need kinematics, Newton's laws type stuff. We need energy, and we need momentum, and that gives us all of our tools to understand how a system works. So now we're doing that for rotation. So our definition for angular momentum, the angular analog of linear momentum, is this radius of whatever object we're calculating the angular momentum of crossed with the momentum, the regular the regular linear momentum. So, like the moment of inertia and the torque, the angular momentum is defined along with a given position. That is to say that it matters where we put our coordinate system when we are talking about angular momentum, right? And we saw that also when we were talking about moment of inertia. Cat's awake. So, for example, if I draw my coordinate system like this, x, z, y, and I have a particle moving with some momentum this way, this has zero angular momentum defined in this coordinate system because I take my r vector, I should have drawn this a little bigger, but I take my r vector from the origin to that object is moving linearly away from the origin. So the r vector and the p vector are always parallel, therefore the cross product is always zero, therefore I have angular momentum 0 for this system. Now, if I just grabbed my coordinate system and moved it down, right, suppose I still had that same particle going like this, I'll draw it a little bigger this time, but now I move my coordinate system down here, as this object moves, right, I'm going to go through different r's, right? It's going to subtend as it moves some angle theta there, right? And so that theta will be the theta that's in our rp sine theta if we were to write the cross product in that way, right? So at some point these are perfectly perpendicular and I get maximum angular momentum. So the angular momentum is not constant here, but it's also not ever 0, right? So all we did was move our coordinate system and we saw that our definition, or rather the result we got for angular momentum changed. So angular momentum is consistent given choice of coordinate systems. For most of the things we'll consider, the choice of coordinate system will be pretty obvious. It will just be dead smack center in the middle of the rotating object, whatever that is. Okay. All right, so that's actually all I wanted to get through in this lesson. Like I said, things are going much more quickly without anybody asking questions. It's also more lonely, so hopefully you go on the forum and sign in there soon and start asking some questions, and I can get on there and answer your questions, and we'll have a little bit of, social interaction for those of us that live alone in an apartment with a cat and are under quarantine orders. So. All the best, and I will talk to you guys soon. Bye-bye.